Welcome back. In this lecture, we will continue the review of the properties, continuing from the previous lecture on the properties. So, we will start with the ideal gas equation of state. Now, the ideally from the perspective of thermodynamics, we would prefer to have analytical equation of state where it represents the state in terms of various different thermodynamic properties such as PVT. Okay, and one of the classical example is basically ideal gas equation of state. So, let me just first formally define what is an equation of state. Any equation that relates the pressure, temperature and specific volume. Okay. So, this essentially will be your equation of state. Okay. So, equation of state is nothing but some function which relates PVT. Okay. And the simplest and the best known equation of state is ideal gas equation of state. In principle, at low pressure and high temperature, all gases approach ideal gas behavior. Okay. So, typically gases behave like ideal because these conditions the gases does not have any effective interaction between themselves, and essentially there is no energy. That means it can have a kinetic energy, but it cannot it does not have any potential energy. Okay. So, such a of course gross approximation for gases does wonderfully work in certain range selective regions, and something which we will be talking about it. So, what is the equation of state for ideal gas is nothing but PV is equal to nRT. Okay. Where n is of course number of moles, R is a gas constant and T is the temperature. Okay. Now, of course, we cannot represent properties of many different substances by simply ideal gas equation of state, and thus for real fluids there are many equation of states which has been developed. One of the classical one was due to Wonderwall. Okay. So, Wonderwall equation of state in early 1930s. The famed equation included the terms related to attractive forces between the molecules and effectively the volume of the molecules. So, this due to the attraction, due to the volume, and thus if you consider an ideal gas, this is going to be 0, A is equal to 0, B is equal to 0, and you are going to get the same equation as an ideal gas equation of state. Now, in order to obtain the parameters A, B for different fluids, okay, one can consider PV plot, and we know that at critical point there is inflection point or critical point is represented by the inflection point. Thus, the criticality or the critical temperature and pressure can be used to evaluate the properties or evaluate this constant A and B. So, using these two equations for the critical isotherms, we can obtain the values A and B, and thus you can use equation of state for many different substances. If you know the critical point of the substances, you can directly get A and B for a specific fluid or gas, and thus you can find out the equation of state, Wonderwall equation of state for a specific gas. Now, of course, including only this attractive force and this size is not good enough. Okay, and thus the accuracy of the Wonderwall equation of state is often inadequate, and this is the reason that many different equation of state have been developed. Okay, and these listed are just like Berthollet, Redlich, Kwang, and so forth. Okay, Peng-Robinson equation of state also. And so, I will not describe in all details. Okay, something which we can use it, and some aspect we will be using in the later part, but there are many different equations of state. Okay, some are popular. Okay, and some are very specific. For example, Peng-Robinson equation of state is one of the most popular equation of state for chemical systems, particularly using ideal gas. So, this is an example where the gauge pressure of an automobile tire is measured to be 210 kilopascal before a trip and 220 kilopascal after the trip at a location where the atmospheric pressure is 95 kilopascal. So, that means the total pressure P1 is equal to 210 plus 95 kilopascal, and P2 is 220 plus 95 kilopascal. Okay. And what is being said that assume the volume of the tire remains constant and the air temperature before the trip is 25. Okay, so it's 25 plus 273.15 Kelvin. Okay. Now what we need to find out is T2. Okay. Now this temperature 25 degrees Celsius is way above the critical point, and it can be considered as an ideal gas. So considering A as an ideal gas, we can simply use P1 V1 is equal to N T1, P2 V2 is equal to N T2, and thus since the volume is constant, P1 by P2 is equal to T1 by T2, and you can find T2 from this simple relation. Okay. You can plug these values in order to get the T2. So of course, ideal gas equation makes life easier in terms of its application, but it works out to be quite well. Okay, even if you use equational state, very complex 8 constant equations, 9 constant equations, 5 constant equations, the value may not change for this particular example. Okay, but maybe it may change if the conditions are well below temperature, so where it can be let us say a saturated system and so forth. So as I said, our intention is to have some kind of equational state, but many times we fail, and for complex molecules it is extremely difficult to have a formulation with a function or an equation which relates PVT for all conditions, and thus property table is more popular for very commonly used fluids such as water, refrigerant. Okay. So therefore, the properties are frequently presented in the form of tables. Now there are some properties which can be measured easily, but others such as entropy and so forth, you need to use some kind of relation from the measurable quantities in order to evaluate such a function. Okay. So in a usually what we do is we measure and calculate all these properties. Some are easily measurable, some are dependent on the measurable quantity and present in a table which in a convenient form. So one of the property is enthalpy, which is often encountered in control volume cases. So typical table will look like this. Okay, this is a table of saturated water, where we say is a pressure table. The reason for that is that the first column is a pressure, corresponding table is saturation temperature of this, because it's saturation water, so saturation temperature, and then you have saturated liquid, vapor, saturated liquid internal energy, saturated vapor internal energy, and the difference of that. So Ug minus Uf is Ufg, and similarly that for enthalpy. Okay. So to give an example here, you have a case where the tank contains a saturated liquid at 90 degree Celsius. So essentially on the TV diagram, since T 90 degree Celsius is less than critical point and is saturated, so it will be somewhere below here, but what would be the corresponding pressure for T 90? So we will look at specifically saturated water temperature table, where the temperature is the first in the column. So corresponding pressure will be your saturated pressure. So here is the temperature and the corresponding pressure is 70.183, and this is where the system is. Okay, this is where the system is, because it's saturated liquid. Okay, it's not saturated vapor liquid, otherwise it would have been somewhere in between, and it is not certainly the saturated vapor, otherwise it would have been here. Okay. So as I said, for a given pressure and volume table or temperature volume table, these 2 points at the end, one corresponds to saturated liquid, one corresponds to saturated vapor. For the case of let us say 100 kilopascal, you have a saturated liquid here and saturated vapor. Of course, we will have a different volume which will be substantially larger than the one contained by saturated liquid. Okay. So for a case of 100 Pascal, you will be looking at a pressure table. Okay, so for 100 Pascal, this will be your saturated Vf. So Vf is this, and saturated Vg saturated vapor volume is going to be Vg, which will be 1.6941 meter cube per kg. So, this is how we try to make use of the table in order to evaluate the volumes and other properties. Similarly, you can also find the corresponding UF here, UG here, HF here, HG here, okay, from the same table. Okay, so what about when the system is at two phase mixture, that means vapor and liquid both, so that means within the saturated regions. So, in order to define such a case, we need to find out the quality of it. So, quality is basically the relative amount of liquid and vapor, and the way it is represented is the mass ratio of the mass of the vapor in the system, that means ratio of the mass of the vapor and total mass. Okay. So, the total mass will be your m liquid plus m vapor, mf plus mg, and x is equal to m vapor. Okay. So, one can show clearly that having this definition, okay, where m total is equal to m fluid plus m gas, and x is m gas by m total, one can show that the average volume of the system is nothing but Vf plus x multiplied by Vg minus Vf. Okay. And similarly for internal energy, similarly for enthalpy. Okay. So, where x in terms of the volume is going to be the Vg minus Vf divided by Vfg. Now, from the point of view of a plot, if you look at P or T versus V, you can use the diagram to find out x also. For example, if V is at which our system is, then we can use the length from A to B and A to C in order to get x here. So, this is directly from this expression. Okay. Now, in general, you can write any property y average as y f, which means the property y of the fluid plus x multiplied by yfg, or the difference between the property y in the gas phase, saturated gas phase, and minus saturated liquid phase. So, in general, y average is going to be in between y f and yg. Y could be v, u, or h. Okay. So, that is what we say here. Okay. So, let me just make use of this understanding to do a simple example. A rigid tank contains 10 kg of water at 90 degrees Celsius. If 8 kg of water is in the liquid form and the rest is in the vapor form, determine the pressure in the tank and the volume of the tank. Okay, so, what we have is information is that it is at 90 degrees Celsius and the total mass is given as 10 kg, 8 kg is in the liquid form. So, that means the mass of the vapor is 2 kg. So, x is 2 kg by 10 kg, this is going to be 0.2. Okay. Now, we have been given 90 degree and certainly it is a saturated system. So, we are going to look at saturated water temperature table, okay, which gives you the temperature, and the corresponding pressure is this. So, P sat of the tank at 90 degrees Celsius is 70.183 kilopascal, right. Now, what is the volume of the tank? So, volume of the tank, we can simply use this information that the Vf and Vg is this. So, V is Vf plus x Vg minus Vf, that is of course Vfg. So, we can write down here 0.001036 plus 0.2 multiplied by 2.3593. Okay, so, that will get V here in terms of meter cube per kg. Now, in order to get the volume, we need to multiply V by 10 kg. Okay, so, this is nothing but V average, right. So, V average by into 10 kg, and that will give us the volume of the tank. So, tank volume. Okay. So, a simple way of using the tables to get the information for for this case. Okay. So, so let us continue further with another example. A mass of 200 gram of saturated liquid water is completely vaporized at a constant pressure of 100 kilopascal. Okay, and we have to determine the volume change and the amount of energy transferred to the water. So, what we have is a mass which is 0.2 kg, okay, and the pressure is given here. So, now essentially since the pressure is given here, we are going to make use of the saturated water constant pressure table, and since it is already informed that there is a complete vaporization, so it is going to be saturated system. Okay, so on a PV diagram it looks like this. So, it is 100 kilopascal and it is being said that it is completely vaporized from here to here, and we have been asked to find out the change in the volume from this to this, and as well as the amount of energy transferred within this. Okay, so that means what would be the difference here also. Okay. So, we can directly take a look at the tables. The tables are given here. 100 is given here, pressure kilopascal, corresponding Vf is here. So, of course, the Vfg is 1.6941 minus this, and the internal energy is given, the difference between the gas and liquid is already given here. So, we are going to directly use this. Okay. So, that means the volume is 0.2 multiplied by 1.6. So, let me say again 1.6941 minus 0.001043. Okay. So, that is going to be the volume of the system, whereas U is going to be 2.088.2, which is nothing but UFG multiplied by 0.2, and that will be your kilojoules. Okay. So, that is the delta U transferred in the system, and this will be your delta V of the change in the volume. Okay. So, this is an example of using the saturated water tables. Now, of course, many times we obtain phases where it is a superheated, which is basically this region. Okay. Now, superheated region is on the right side of the saturated vapor line. Okay. So, the way to represent or to find out this superheated, whether the system is at superheated, let us say at a constant pressure, is by looking at its property, which should be greater than the saturated property. If this is the saturated vapor point, then the corresponding, let us say, enthalpy is Hg. Then if the system which is at superheated condition, the enthalpy of that is going to be greater than Hg. So, for this also we have tables. Tables are typically in terms of V, U, H and temperature for a given pressure. Okay. So, that is how we make use of such a superheated tables in order to solve problems related to superheated conditions. So, let us look at an example. So, here we have a system which is at state where the pressure is defined and enthalpy is given, and we need to find out the temperature. Now, since we do not know whether the system is at superheated or saturated or compressed, we need to first find out what is the possible state of that. So, the best way to do this, to make use of first the condition of saturated water pressure table, where we look at the condition here 0.5 megapascal, which is 500 kilopascal, and look at the corresponding enthalpy of the vapor. Okay. Now, 2890 is certainly more than 2748.1, that is H is greater than Hg, and thus it is in the superheated vapor condition. Okay. So, thus we should directly take a superheated water tables. So, there are many values. We have to pick up a condition where we should get P is equal to 0.5 megapascal. So, we take a values corresponding to P is equal to 0.5 megapascal, and here you have VUH. Okay, so this is like VUH and the entropy. Okay, so we will talk about that later. So, within this we look at the value H is equal to 2890, and we can see that H is equal to 2890. So, this is our H here, lies between temperature 200 and 250, because 2890 is in between here. So, that means temperature is in between this. Now, in this case, in order to find precisely the temperature, what we are going to do is we are going to do a linear interpolation. Okay. So, a very simple way to do that is we consider the difference in the this two temperature 250 and 200, okay, and the slope of the linear line from 250 to 200 will be the same as that in the temperature in between to 200, and that is what we are going to use, that delta H divided by the temperature, and from here we rearrange this to get this temperature, which comes out to be 216.3 degrees Celsius. Okay. So, what we are looking at is simply the slope of the line from this 2 point. Okay. Okay, so this is a common way of solving problems where the data are not given for each point. So, we make use of linear interpolation. Okay, so in addition to superheated vapor, which is on the right side of this saturated vapor line, you have a compressed liquid which is on the left side of a saturated liquid line on a P or T versus V plot. Okay. So, a compressed liquid line, usually what we consider is for a given point somewhere, let us say here, which is on a P is equal to 500 kilopascal at temperature 75, the property we approximate to that of the liquid, saturated liquid at the 75 degrees Celsius. Okay. So, usually we approximate, because the compressed liquid property depend on temperature more than on pressure. Okay. So, in this case the pressure variations are usually neglected, but for enthalpy, for example, the more accurate relation is given here. Okay. So, this is something which one can derive using thermodynamic relations, and which we will be doing it in the later part of this course. Okay. So, what are the conditions for the compressed liquid? So, for corresponding to 75 degrees Celsius, the saturated point is here, and at this point, so this will be your P sat, okay, at that temperature of the system. Okay, this is a P sat at the temperature of the system, which is 75. Okay. So, basically the system is at 75 degrees Celsius and 500 kilopascal. Okay. So, if you look at it, the pressure P here is greater than P sat at T. So, that is the condition which we have, P should be greater than P sat at a given temperature. In addition, the temperature, if you look at it, for a given pressure, the T sat for this P is 151.83 and 75 is less than 151.83. So, the temperature is less than T sat at a given pressure. Okay. So, in general, these two conditions will conclude that it is a compressed liquid, but in general all the properties such as your specific volume, internal energy, enthalpy will be less than the corresponding properties of the fluid at a given pressure or temperature. Okay. So, that is how we define compressed liquid. So, let me now talk about the deviation of the properties from the ideal gas behavior. As we said that we are interested much to represent the properties or the state of the fluid in terms of some kind of equation of state. So, one way to look at is how much is the deviation from the ideal gas. Is it possible to quantify the non-ideality in terms of very simple parameters, and that is what the compressibility factor talks about it. So, the compressibility factor can be represented in terms of PV is equal to ZRT, okay, where this is a molar volume. So, Z basically represent deviation from non-ideality For ideal gas, Z is equal to 1. For real gas, it could be less than 1 or greater than 1. If you decrease the pressure such that it is 0, where the particles are far apart, it will start behaving ideal gas. Okay. So, what is the definition in general for low pressure? It need not be like going to 0 or absolute 0, but in general Z is unity when the gases are at low pressure or a high temperature. So, but what is the definition of low pressure and high temperature? It is with respect to its critical point. So, the low pressure high pressure of a gas is high or low relative to its critical temperature or pressure. Okay. So, in practicality or in general, you on a TV diagram, this region would behave like ideal gas behavior because it is extremely low pressure, because so it is extremely low pressure, right. So, the pressure will decrease here, right, and as well as this pressure because the temperature is quite high. Okay. So, these two regions will start behaving more or less like ideal gas. Okay. Now, the other important thing is now it was noted that if you reduce the properties such as your pressure, temperature and volume by its critical point, then many substances who have similar type sizes, they start behaving similarly in a reduced plot. Okay, and this is the principle of corresponding state. Okay. So, if you reduce pressure by its by the critical point of the fluid and get a variable PR and similarly TR and VR, we can plot Z as a function of PR for different TR, and it appears that the many different substances which is here written here, methylene, ethylene, ethane and so forth, they all fall on almost similar on the same curve. Okay. This is what is beautiful, because essentially it tells you that if you take out the characteristic property of the molecules in the form of the critical point, then all behave similarly. Okay. So, thus you can map this on a single curve which we call it compressibility chart, and which is nothing but the Z here as a function of PR. Now, you can clearly see here Z can be less than 1 as well as in certain condition it will be more than 1. Okay. So, if you want to find out Z, just using the compressibility chart is quite easy for a given fluid. For example, in this case any of this, you need to find out for a given P and let us say for given T. Okay. You can get PR and TR using its critical point, and then for a given TR, for a given PR and TR, you know exactly this line, and then you can take Z, and from there you can find out other properties. Or for that matter, if the Z is given and a specific temperature is given, let us say, you can use that in order to get the other unknowns. Okay. So, this is how the compressibility chart is used. Now, this is a simpler compressibility chart. There is more complete compressibility chart for many different systems. This is something which we call it Lensel-Obert generalized compressibility charts, and it is designed such that it has a specific chart for low pressure and high pressures. Okay. And here you can find out that it can go, the Z can also deviate from 1. Now, in addition to PR and TR, you have also VR in this case in order to simplify this exercise. Of course, this is something which is commonly used in industry, and one can also do an exercise on it, which I leave it to you. So, this was a very quick introduction to properties, particularly the phase diagram, utility of the tables and equational state. We will continue our discussion in the next lecture. Okay. See you in the next lecture.